This conference will now be recorded.
Hello everyone. Today we will see the test of the applications of electrochemical series. Two applications we have already seen in the last class. And today the test of the applications we will discuss. And after that, if there is time left, then we will see what is cell potential and how Gibbs free energy that is related to cell potential. So number 3 is displacement reaction. So with the help of electrochemical series, we can predict whether displacement reaction can take place or not. So here we have a general example for displacement reaction. So suppose we have started with the starting material A and BC. So here B and C, this is the bond between B and C that is broken, and C is now attached with A. That means C is replaced by A. So that is why it is example of displacement reaction. So how to predict whether a given metal that will displace another metal from its salt solution. So suppose we have any metal here and another metal is M prime X. So in the product what we will get? M prime and Mx. So this is the example of displacement reaction. So here it is in zero oxidation state, but M prime that is in +1 state. But after reaction, now M prime is reduced from +1 state to 0, and M0 that is oxidized to +1. So here this type of oxidation reduction, that is redox reaction, will take place or not, that we can predict with the help of electrochemical series. The metal which is having low standard reduction potential, that will displace the metal from its salt solution. So here if we want this reaction to occur, then the reduction potential value for M plus M system, it must be lesser compared to the other system which is M prime plus M. So then only this reaction, this displacement reaction is possible. So higher value for M prime plus M. Now if we look at the reaction example, we have started from zinc and Cu2 plus. So here this is M and this is M prime 2 plus. Okay, so zinc, whether it will be converted to Zn2 plus, that is oxidized to Zn2 plus, and Cu2 plus is reduced to Cu0, that will take place or not, that we can understand from electrochemical series. So here we have taken copper sulfate aqueous solution which is blue in color, because copper 2 plus in aqueous medium it is blue in color, and we have dipped a zinc strip. So zinc, it is zero oxidation state. Now if the reaction is taking place, that means now copper 2 plus that will be converted to copper. So now you can see the color of the solution, it is faded. Here the color is intense, but here it is faded because now the gradually the Cu2 plus concentration is decreasing and copper will be deposited in this way. So this is metallic copper, and the size of zinc strip that will gradually reduce because zinc is oxidized to Zn2 plus. So now it is no longer metallic zinc, so that is why it will reduce in size. So this reaction, it is actually possible because here Zn2 plus Zn system, it will have lesser value, that is standard reduction potential value, compared to the other system which is Cu2 plus Cu. As this is lesser, that is why this reaction is possible. But if we are doing the opposite reaction, that is suppose you have dipped a copper strip in zinc sulfate solution, then the opposite reaction, that is deposition of Zn from Zn2 plus to Zn on this metal strip, that will not take place. Okay, because the reverse reaction is actually possible, so this is not possible. So is there any doubt? So this is also displacement reaction example. Next slide, this is also another displacement example, because displacement reaction, it may be different types. In the previous case you have seen metal is displacing another metal, but now what we will see displacement of hydrogen from dilute acid by metal. So this is also another type of displacement. Here, suppose the metal is M and there is any acid. Suppose we have taken HCl. So here H is in +1 state. Now if M is having lesser reduction potential value compared to H plus H system. Now H plus H system, we know it is standard hydrogen electrode, which is by IUPAC convention we consider 0 volt value for this system. So if metal is having lesser value than 0, that means negative value, then metal will be able to displace H from Cl. So ultimately what will happen, it will be removed as H and two H atom together, it will make hydrogen gas. Okay, and Cl will be Cl minus and it will form salt with Cl like MCl. So this type of displacement of hydrogen is possible. So hydrogen from plus state, now it is reduced to H0. So this is reduction. Metal is acting as reducing agent here. The metal which can provide electrons to H plus, that means it is acting reducing agent. It is feeding electron to H plus system. Present in dilute acid. H plus ions which is present in dilute acid. If you take H2SO4, then also there is H plus. So it can provide electrons to H plus ions which is present in dilute acids. That is reduction is going on, and it can evolve hydrogen from dilute acids. Now, if we look at these examples, here we have taken three different metals, Mg, Zn, and iron. Now, see, in the first case, the reaction is very vigorous. Okay, fumes are observed. In the second case, the reaction rate is moderate, slight fumes you can see, but in case of iron, there is no reaction at all. So, gradually, as we are moving from Mg to Zn to Fe, the reaction rate is decreasing. That means Mg will have more negative value compared to Zn, and Zn will have more that is lesser value compared to Fe. So here standard reduction potential value, if we compare among these three, from this observation it is clear that iron system will have greater potential compared to Zn, and Zn will have greater potential compared to magnesium. So here this magnesium, it can replace hydrogen from acid very quickly. In case of Zn, it is moderate reaction rate, and in case of iron, it is very slow. Okay, so these are the examples for displacement of hydrogen from dilute acid. Another type of displacement we will see now. What is the type? This is the displacement of one non-metal from its salt solution by another non-metal. So until now we have talked about only metals, but now we will talk about non-metals. So when it is non-metals, obviously plus positive oxidation state is not possible. So now we will have negative oxidation state and 0. So suppose if you consider halogen, it will be 0 or it may be X minus. So this is the that is 0 state, this is negative state. That means if X is converted to X minus, that means it is reduced. Okay, so suppose we have two non-metal. One non-metal, it is existing as X2, and another non-metal that is in the salt form. So suppose it is Mx prime. So this is another halogen or any non-metal. So here non-metal which possesses high positive reduction potential. So among X and X prime, suppose one of the halogen, it is having, not halogen, I mean non-metal, it is having high positive reduction potential. So the system which will have high reduction potential value, it will have a tendency to accept electron. That means it will act as oxidizing agent, and readily electrons, it will accept electron readily, and it will displace another non-metal with lower reduction potential. So here suppose X is having high reduction potential value compared to X prime, so X can remove X prime and it will take the place of X prime. So now it is Mx. So X prime here, it is in -1 state, but after displacement it will be oxidized to X prime 0. That means now we will get X prime 2. Now look at these examples. Here we have taken KCl, KBr, Ki, and in the left hand side column, chlorine, bromine, iodine. So when chlorine is added to KCl, there is no reaction. When chlorine is added to KBr, then what we are getting? Potassium, that is KCl plus Br2. And when it is added to potassium iodide, then what we are getting? We are getting iodine and KCl as product. So it means what? Chlorine can, obviously chlorine when added to potassium chloride, it is same system. So no question of reaction. Chlorine when added to KBr, now Br minus, that will reduce Cl to Cl minus. So after reaction now it is -1, and Br minus, that is oxidized to bromine 0. Similar, so here we can say chlorine is acting as oxidizing agent. It is oxidizing Br minus. Similarly, chlorine can also oxidize I minus to iodine. Next, if you take bromine, bromine cannot oxidize Cl minus system. Okay, because chlorine is having higher reduction potential value compared to bromine, and it is similar system, so we will not consider it. But bromine can oxidize potassium iodide to iodine, that means I minus to I2. And for the last system, iodine is basically among these three halogen, iodine is having the least value. So here Cl will have high reduction potential, then Br, and then I. So as it is least, so that is why it has no capacity to reduce the other system. Sorry, not to reduce. I mean, that is, it will get itself reduced. So it cannot act as oxidizing agent. It can't act as oxidizing agent. Okay, because it has very among these three, it has least value. So these are the examples of displacement of one nonmetal from the salt solution by another nonmetal, because Cl, Br, I all are examples of nonmetals. So these two examples, is there any doubt? That is this displacement of hydrogen from acid and the second displacement of nonmetal. Is there any doubt? Should I repeat? Now the last type of displacement that we'll see here is displacement of hydrogen from water. Okay, so in water, the oxidation state of hydrogen, it is +1. Now if hydrogen is removed in the form of H2, that means from +1 it is again converted to H0, that is reduced to H0. Iron and the metals having more negative EP value, electron potential value, they are capable of liberating hydrogen from water. That means these metals, iron and the metals having more negative EP value, they are capable to reduce H plus to H0. That means they can liberate hydrogen from water. But if you take alkaline earth metals, that is sodium, magnesium, calcium, etc., they can liberate hydrogen even from cold water. But Mg, Zn, and Fe, though Mg is actually also alkaline earth metal, but this is exception. So these elements, these two are from D block, they can liberate hydrogen from hot water. Okay, now see what is the difference. Actually, iron and the metals having more negative EP. So these alkali and alkaline earth metals all are having negative EP because they are very active metals. That means their reducing power is very high. But the reactivity, that may vary. So when it is alkali and alkaline earth metals, basically cold water is okay. Even they can react with cold water. But if you have taken Zn or Fe, now you have to provide hot water or steam if you want any reaction, because compared to sodium or any other alkaline or alkali metals, potassium, lithium, these metals, their reducing capacity is less. So that is why now we have to use hot water or steam. That means extra energy we have to provide. So if you look at this reaction, sodium is reacting with water. In the bracket, physical state is L. That means it is liquid water. And we are getting NaOH and hydrogen gas liberated. But if it is iron, then you need steam. Okay, so that is the difference. Next example, that is application is, so in case of iron, I'm just saying that if you are using iron and water, you have to take water in gaseous form. That means now it is steam. So that is why I have written G here. Fine. But in case of sodium, liquid water is okay. That is cold water. Number 4 application is extraction of metals. A more electropositive metal, it can displace a less electropositive metal from its solution, that we have already seen, okay, in displacement reaction. Now this principle we can apply for extraction of some metals. For example, silver and gold by cyanide process. So in this process, what we do, silver from the solution containing sodium argentocyanide. So this is for molecule sodium argentocyanide NaAgCN2. So here oxidation state of silver is +1, sodium is also +1. So these two plus charge, that is balanced by 2 cyan, because cyan is having single negative charge. And we are using Zn. So here Zn will reduce silver to silver 0. And itself it is taking the place of silver. So now it is 2 sodium plus, that means 2 plus charge, and for zinc it is 2 plus, so 4 positive charge is balanced by 4 cyan. Here silver is reduced to silver 0. So in this way we can extract silver, that is metallic silver, we can extract by using Zn as reducing agent. So here Zn is more reactive compared to Ag, and remember the reduction potential value, if you compare, obviously Ag system, that is Ag plus system, that will have higher reduction potential value compared to Zn2 plus Zn system. So that is why this reaction is possible. Here zinc is acting as reducing agent and itself is oxidized to Zn2 plus. This is number 4 application. The next application is very important, which is corrosion treatment. So for corrosion, that is to prevent corrosion, we can take the help of electrochemical series. But before that, we have to understand what is corrosion actually. Okay, it is in daily life, it is a very common example. So it is the chemical process of deterioration of any material. So here in that is corrosion, it is a very broad term. But what we will focus on rusting process, because rusting is one also that is one of the example of corrosion. The most important by far is electrochemical corrosion of metals. That means suppose if any metal it is in metallic form, now it will be oxidized to M plus. Not just M plus, it may be any other positive charge also. And electron is removed, and this oxidation is facilitated by the presence of suitable electron acceptor. And when we are considering, that is when it under normal condition, the most good oxidizing agent, obviously it is oxygen, which is present in air. So for rusting process, basically we need water as well as we also need oxygen, because here oxygen will act as oxidizing agent. So what happens in case of corrosion? We know that for iron we use the word rusting. So if there is any iron material, what will happen? Suppose this surface area, you can see this is very smooth surface area, but in this surface area we have a crack. So where there is a crack, oxygen, that is basically air, oxygen is coming from air. So air can come in contact with the smooth surface very easily, but if there is any crack or narrow space, oxygen cannot reach that place very easily. So as a result, what will happen? This system, that is O2, is converted to H2O. So this process is basically, see, it is reduction process. Why? Because O2 is 0 oxidation state, but in water, it is having -2 oxidation state, that is oxide. So this smooth surface of iron, it will act as cathodic site. That means here reduction reaction will take place. So for reduction, obviously we need electron. So where from the electrons are coming? It is coming from this cracked region, which is acting as anode. So electrons are coming from this region, and how it is coming? It is coming because iron is now converted to Fe2 plus and 2 electron removed. So these electrons now will oxygen will accept, and it will be converted to O2 minus from 0 oxidation state. So O2, it is accepting electron and it is converted to water. Okay, and ultimately this Fe2 plus, which is produced from iron, that is, this is oxidation obviously. So this Fe2 plus, that in presence of water, sorry, that in presence of oxygen, it will form this type of oxide, that is Fe2O3, and also there is some water, X number of water molecules. So water is also present. See this total, this is actually a drop of water. This is the enlarged picture. Fine. So basically this is the, as if this type of system we have seen in case of cell diagram, right? That is, there is anode electrode, cathode electrode, but this is a natural example of cell. So the same iron, one area is acting as anode, another area is acting as cathode. Okay, and Fe is oxidized to Fe2 plus, and oxygen is reduced to oxide ion, which is basically H2O is written, but actually here O2 minus ion is present. Fine. So these two are the half cell reaction as if, and ultimately the product that is obtained is Fe2O3. So as a result, what will happen? This narrow cracked space, that will be there will be corrosion more and more. So ultimately this space, there will be, that is total iron that will be removed in the form of Fe2 plus. So this is the corrosion process, but we can prevent it. So how we can prevent it? So the very common way is to protect with the help of steel, or sorry, protecting steel. Steel is basically iron. Okay, iron is also present in steel. So if we want steel to protect from corrosion, what we will do? We will coat it with zinc layer, and this process is known as galvanizing. Now why we are doing so? Because Zn2 plus Zn system, and if you compare with Fe2 plus Fe system, this is more reactive. That means this system is having higher reduction potential value. So that is why now when Zn is present, it will act as sacrificing element. Why? Because now oxygen, this that is reduced to O2 minus, this reduction, for this reduction we need electron. Now Zn will supply this electron because Zn is more reactive compared to iron. So that is why it will act as we will call it sacrificial coating. Why sacrificial? Because it is sacrificing itself for the sake of iron. So iron now will be fine. There will be no reaction on the surface of iron, but as there is zinc coating, so obviously zinc will be preferred if you compare between Zn and iron system. So the zinc coating, it is being less noble than iron. Less noble means it is less inert. It is more reactive. It tends to corrode selectively. So dissolution of the sacrificial coating leaves behind electrons. So now what will happen? See, look at this picture. Now on the surface of iron we have zinc layer, right? And zinc, that is Zn, it will be converted to Zn2 plus, and electrons will also be there. So these electrons, now there will be accumulation of electrons. So negative charge accumulation on the surface of iron, it will inhibit the dissolution of Fe2 plus. So now these electrons, it will be accepted by oxygen and it will be converted to oxide. So iron is now intact. There is no reaction going on with iron. Okay. Now there is another example, and what is this line is saying? That coating leaves behind electrons which concentrate in the iron. So there is now accumulation of excess negative charge, making it cathodic. Cathodic means in cathode we know reduction reactions going on. So if there is accumulation of electron, it will be cathodic in nature because it will be able to supply electron. So as a result, dissolution of iron will be inhibited. But suppose instead of zinc layer, you have given tin layer, Sn. Now Sn system compared to iron system, it is more noble. That means iron is more reactive compared to Sn. So if we compare these three metals together, it is like Zn, then Fe, then Sn. So if you have given a tin layer on the surface of iron, what will happen? Now tin will act as, that is, it will just act like oxygen. So there will be more and more corrosion. So when there is actually no layer, the corrosion that you are getting, in presence of tin layer, the corrosion will even increase, because now there are two electron accepting species. Oxygen is already there present in the atmosphere, and now you have given tin layer. So tin is also capable to accept electron from iron. So as a result, iron will be corrode very easily, because oxygen will also accept electron from iron. Iron means Fe0. Tin will also accept electron from iron. So as a result, there are two, as if two cathodic side, that is, here we can see one cathodic side, so here as if it is two cathodic side. So now corrosion will even increase. So that is why zinc is used for this coat, for coating steel, so that we can protect it from corrosion. Okay, so is there any doubt? Number 6, checking spontaneity of a redox reaction. So if the reaction is spontaneous, suppose any cell diagram is given like this, and it is asked that predict whether this cell reaction, it is actually possible or not, that is practically possible or not. So how to predict that? If it is spontaneous, then it must have positive potential. So these two are two half reactions, and we know if we want to find out the net E0 cell of the reaction, that is standard reaction potential of the cell, what we do? We take E0 for cathode. So this is cathode system, this is anode system, minus E0 of anode system. So if this value is positive, then only it will be spontaneous, but if it is negative, it will not be spontaneous. So from electrochemical series, for each system you can get the corresponding E values, and if you know the E values, just do this calculation. If you are finding it positive, it is spontaneous. If it is negative, it is not spontaneous. Okay. So for this cell representation, we have Zn SO4 system in the anode system. That means here Zn will be converted to Zn2 plus, and Cu2 plus will accept this electron which is coming from Zn, and it will be reduced to copper plus 2 electron. Okay, so this reaction, is it possible or not, that we can predict with the help of electrochemical series. So if you look at this electrochemical series, here these two systems, first of all we have to find out. So this is Zn2 plus system, the value is minus 0.76. So this value is minus 0.76. And for copper, see, the value is plus 0.34. That means this is 0.34, and there is a negative sign. So negative will be cancelled, and ultimately this value will be positive. So this reaction is spontaneous, that you can predict from the help of electrochemical series. Okay. But suppose if it is opposite, that is copper system is present in the anode and zinc system is present in the cathode, then obviously the value now will be negative, because in this case E0C minus E0A, it will be minus 0.76 first, then minus 0.34. So obviously as it is negative, this reaction is not possible. So this cell representation is correct, but if you do the reverse, it will not be correct. Okay, that is not correct means, I mean to say, it will not be practically possible. Okay, so this is number 6, that is you can check the spontaneity of any redox reaction. Redox, why? Because they are both reduction and oxidation. This is oxidation and this is reduction, both are going on, and the combined cell reaction will be just add these two equations, number 1, number 2. So you will get Zn plus U2 plus Cu plus Zn2 plus. Okay, electron will be cancelled. Now we have a problem based on these concepts. Standard reduction potential value for these three systems, Zn, nickel, iron, these are given minus 0.76, minus 0.23, minus 0.44 volt. So all are minus. Now suppose we have a reaction X plus Y2 plus. Now X is oxidized to X2 plus and Y2 plus is reduced to Y. So this is reduction, this is oxidation. So this reaction will be spontaneous for which of this combination? That we have to predict. And this is single choice answer, so only one of the options will be correct. So in the first case, X is nickel system. That means nickel will be converted to nickel 2 plus. So this is acting, this will be in the anode side, that is oxidation. And iron is reduced to Fe. So this will be in the cathode side, that means it is reduction. So the E naught value for the cell, it will be, first we will write the reduction, that is we will write the reduction potential for the cathode system. So this is actually cathode. So for iron the value is minus 0.44 and for nickel the value is minus 0.23. So ultimately it is 0.44 plus 0.23. So see, this value is high. So ultimately it will be negative. Even you don't have to do the full calculation, it will save your time. Because you just need the sign of this value. You don't need the actual value. So as it is negative, without calculation you can understand this is not possible. In case of now X is also nickel, but Y system is changed. So in the second case, E naught cell will be, first you have to write the reduction potential for the Y system. So now Y is Zn and Zn having value minus 0.76, for nickel minus 0.23. So again this will be positive, that is minus minus it will be positive. So ultimately what you are getting, this is also negative. So this is not possible, not spontaneous. Now for the third system, here Zn is fixed. So E naught cell, I'm just writing in this way, minus 0.76 and for iron it is minus 0.44. So see, again it is minus 0.76 plus 0.4. So again it is negative. Obviously not possible. Now if you are lacking time, you can easily understand that this is the right option, but we will do the calculation here. So now the cathode system is nickel. Nickel is minus 0.23. Cathode system first we have to write and then the potential value for the anode system. So for Zn it is minus 0.76. Now it is positive, right? So as it is positive, this reaction will be spontaneous. So when X is Zn, Y is nickel, the reaction will be Zn Ni2 plus, Zn2 plus and nickel. So this is reduction, this is oxidation. So this reaction is feasible because here the E value we are getting positive. Okay, correct option is last option. So is the doubt clear? Is there any question? So I'm going to the next problem. Here we have a cell representation. M converted to M plus, this is anode, this is cathode. E naught value for the anode system given 0.44 volt and for X minus it is given 0.33 volt. So these are the data that are given. So we have to check among these four statements which is correct. The first one is saying that M plus X converted to M plus and X minus, this will be spontaneous reaction. So M plus X product M plus X minus. So is this conversion is possible, that we have to predict. So this system is oxidation, this system is reduction. That means if you want to find out E naught cell, you have to write the reduction potential for the reduction system, which is cathode. This is cathode, this is anode. So for cathode, it is 0.33, and for anode, it is 0.44. So obviously, this is negative. This is not possible. This reaction is not spontaneous. Now see, it is very easy to understand that if you look at the next option carefully, it is just the reverse reaction of the first reaction, right? See, if the first reaction is not possible, obviously the opposite one, it will be spontaneous. So you can easily understand this will be the correct option. Okay. So if there is lack of time in this, try to save your time in this way. Okay. Because if this is not correct, the second one, it has to be correct. So now as the reverse reaction is going on, so for the second one, E naught cell will be 0.44 we will write first, then 0.33. So this will be 0.11, and this is positive. So this is possible. And C and D, you can easily understand it is not correct because this is actually E naught cell because standard reduction coefficient. Okay. So the value is positive, but it is 0.77, but actually the value is 0.11. So this is not correct. This is also not correct. So here single choice, single correct answer, which is option B. Correct option is option B. Fine. Now this question is multiple correct. So more than one option may be correct. Here MnO4 minus is reduced to Mn2 plus. So what is the oxidation state of Mn here? First we will find. So X is the oxidation state. Overall charge is -1. So how to find out? X plus 4 into -2 for oxygen, because for each oxygen atom it is -2 charge. So 4 oxygen atom, 4 into -2. Overall charge -1. So X will be equal to +7. So MnO4 minus, it is converted to Mn2 plus. Oxidation state +7, it is now becoming 2 plus. So this is obviously reduction because oxidation state is reduced to 2 plus. So this process is reduction. So this will be in the cathode side. Now there are some other systems given. Reduction potential for Zn, Ag and gold and sodium. 4 systems. They are given here. Fine. Question is, which of these metals will be oxidized by MnO4 minus ion? So this process is reduction and it is acting as oxidizing agent. So the other system that has to act as anode system, because here Zn will, sorry, it is 2 plus, not +1. Zn will act as reducing agent. It will reduce MnO4 minus to Mn. Then Ag will act as reducing agent, gold and sodium. But is it possible or not, that we can predict from the values? So if we are considering it is MnO4 to Mn2 plus, then Ag to Ag plus, Zn to Zn plus 2 plus, gold to gold plus, and sodium to sodium plus. All these are actually the reactions that are going on in anode because it is oxidation, and this one is reduction from +7 to +2. So as we know that E naught cell, if we want it positive, then E naught C minus E naught A, this value will be positive. Now when it is positive, when E naught C is greater than E naught A. So E naught C is fixed here, which is 1.51 volt. See, this is the value given. And for the other system, the values are, it is almost 0.8. For Zn, it is minus 0.76. Gold 1.69 to, and sodium minus 3.0. So all these are basically E naught C. Okay. So sorry, I have made a mistake. All these are basically anode, E0A, and this is E0C because it is reduction, so it will be cathode. Okay, so in which case E0A is lesser, that we have to check. So 0.8, it is lesser than 1.51, so it is possible. Then minus 0.76, this is also possible. 1.69. So now E0A is greater than E0C, so this is not possible. Gold cannot act as reducing agent here, and sodium it is already negative, so this is possible. So except gold, in other cases, the reaction will be spontaneous because E0C is greater than E0A. So here correct options will be A, B, and D. Gold is not possible, which is clear from this value. So see, don't waste your time by doing the detailed calculation. That is not necessary. You just have to check whether E0C is greater than E0A. But for that, you have to understand which system is actually acting as E0C, that is the cathode system, and which are the anode system. If it is clear, then you have to just check whether E0 for cathode system is greater than E0 for anode system, and if it is positive, then only the reaction will be spontaneous. So which of these metals will be oxidized by MnO4 minus? Oxidized because Ag will be converted to Ag plus, Zn will be converted to Zn2 plus. So all these are basically oxidation reaction, right? So this is oxidation reaction. So here among these four metals, Zn, silver, and sodium can be oxidized to Zn2 plus, Ag plus, sodium plus respectively. Correct options A, B, and D. Is there any doubt? Another problem. Here a cell representation is given. So this is the representation. In the anode side we have Zn system, but in the cathode side we have the general system which is Mx plus 2M. So as M is there, it must be some metal, but different metals are given, that is different half cells, and their standard electrode potentials are given below. So here M systems, it may be gold 3 plus to gold, silver plus to silver, Fe3 plus to Fe2 plus, sorry, it will be here, and Fe2 plus to iron. So total 4 systems are given that may be in the cathode side. This is cathode, this is anode. So these are the values for E0C. All these are E0C. Now E0 for Zn2 plus Zn system, which is in anode, that is given, that is fixed because Zn is directly given, but metal is varying. So 4 different metal systems are given. The last 2 are both iron, but oxidation state is different. Here it is 3 plus to 2 plus, it is 2 plus to 0. So obviously reduction potential value will be different. So which cathode will give maximum value for E0 cell per electron transfer? Okay, so here which of them will be giving maximum value? How to understand? Obviously all these are E0C. So E0C minus E0A, in which case will be maximum, that we have to see. So in case of gold, it is 1.4 minus, then another minus, that means it will be 0.76. For silver, it is 0.8 plus 0.76. See, each time the negative is cancelled and it is positive, and writing directly. Then in case of the third system, it is 0.77 plus 0.76. And in the last system, it is minus 0.44 plus 0.76. And if you look carefully, all are basically positive. So in all cases, reaction is possible. That is, the cell diagram is okay. But we have to find in which case it is maximum. So from these 4 values, can you tell me which of, that is among these 4, which will be maximum? That is, which metal system will act as cathode? This is also single correct answer. Any idea? So 0.76 is fixed. Only there is change in the other value. This is fixed. So the other value, if the more higher the value, the higher will be the total amount. So here in this case you will get max value. So correct answer will be goal system. Any doubt?
No, ma'am.
Okay. So now we have discussed some problems. After that, as we have time, we will see what is Gibbs free energy, which is a thermodynamic term basically, and how it is related to cell potential. So first of all, we have to understand that the magnitude of electrode potential, that is actually dependent on some factors. So these are the factors. So as it is dependent on these factors, so that is why there is a concept of using standard electrode potential. Standard means concentration is fixed 1 molar, temperature is fixed, room temperature 25 degrees centigrade. So two things are when fixed and electrode is already fixed, then only we are getting standard electrode potential. So because of this variable property, that is variables on which magnitude of electrode potential depends, that is why this concept of standard electrode potential is introduced. Now when you are doing actually the cell reactions, it may be that you are not using it at room temperature, you are using, that is the temperature is something else, and the concentration of ions, it is not necessary that it has to be always 1 molar. So in that case, it standard electrode potential value that will not work. So what to do? So now the concept that will help us, that is related to Gibbs free energy, and we have to first understand Gibbs free energy, so that ultimately we can understand that when concentration of ions are not 1 molar and temperature is not room temperature, how we will get the actual cell potential value. But before that we have to, which is basically the use of Nernst equation. But to how we are getting Nernst equation, to understand that, first you have to understand what is Gibbs free energy, that is how it is related to the cell potential E value. Now this variation of electrode and cell potential, basically the variation of cell potential with concentration of the ions, it can be obtained from thermodynamic consideration, that means from the consideration of G. But how it is so? Just look at this expression. This is a general reaction. M1 is the coefficient of A, M2 coefficient of B, N1 and N2 coefficient for X and Y. These two are products. So from A and B starting materials, you are getting X and Y. So suppose this reaction is occurring in the cell. So what will be the Gibbs free energy for this reaction? So the expression is del G equal to del G naught. This is the standard value, and this value is at any temperature and concentration. 2.303 RT log base 10. Now see, in the numerator we have activity of species X to the power its coefficient, activity of species Y to the power its coefficient, N2 and N1. So first we will write the product side, that is the species that are involved in the right hand side, product side, and then in the denominator you will write activity of the two starting materials, and see in the power there is the coefficient. So suppose if it is 2A plus 3B, I am just saying arbitrarily, so it will be activity of A to the power 2, activity of B to the power 3. Now activity for dilute solution, it is actually almost equal to concentration. So this activity terms you can replace it with the concentration terms. That is possible for dilute solution. So this is the expression for del G, but we need the E value, okay, E cell. But for that we have to understand what is the relationship between G and E. So in thermodynamics, because this term we get from thermodynamics, the Gibbs free energy, it is a thermodynamic potential. So why it is thermodynamic potential? Because If you know the Gibbs free energy value, then you can measure the maximum reversible work done that is possible, because maximum reversible work done, that is related to del G, that is decrease in del G value. Now it measures the maximum reversible work done that may be performed by a thermodynamic system at constant temperature and pressure. So how we can get it? That we'll see in the next slide. But before that, so this is related to thermodynamics, that is how G is related to work done. But in electrochemistry, that is the chapter that we are discussing, the maximum amount of electrical work done in galvanic cell at constant temperature and pressure, this is related to cell potential by this relation. So the work done, that is equal to amount of charge, which is NF. And how it is NF, I will describe that. So it is amount of charge multiplied by cell potential. Okay. So E is basically joule per charge that we have seen. E is equal to J by C. Now amount of charge, this is also in coulomb. So coulomb will be cancelled, and ultimately the unit will be joule. So see, in the left hand side we have work. Joule is the unit for work, that is energy unit. So now unit is met. Now what is NF? N will be the number of moles of electron and F is Faraday. So the charge for 1 mole of electron, charge of 1 mole electron is basically 1 Faraday. So if it is 1 Faraday for 1 mole, if there are n moles, it will be NF charge. So total amount of charge multiplied by E cell, that will be the electrical work. So this is actually NF E cell. Okay. Now from thermodynamics we have seen that electrical work, that is if it is electrical work, in that previous slide we have seen in the box that is below, here it is written that the measure of maximum work done by a thermodynamic system at constant TP, it is the Gibbs free energy, decrease in Gibbs free energy. Now if this work done, you correlate it to electrochemical work done. So electrochemical work done, that also we can write in the form of del G, that is decrease in del G value. So this is equal to minus del G. Now in the previous slide you have already seen that the work done, that is equal to NF E cell, but W is also equal to minus del G. So now it means del G, that is decrease in del G minus del G, that will be equal to NF E cell. So ultimately, if it is standard condition, now not sign will be used. So the relationship that we are getting, very important relationship, is that del G naught, that is equal to minus NF E naught of the cell. Okay. So number of moles of electron, Faraday, it has a particular value, which is 96500 coulomb, and E naught cell. So if you know all these values, you can easily find out del G naught. Similarly, you can also find out E naught by dividing del G naught by NF. That is also possible. Okay. So E naught cell, that is equal to minus del G naught by NF. Depending on what are that is in numericals, what values are given, you have to choose any of this equation. If del G naught is given and number of moles are known, then you can easily find out E naught value, E naught cell value. And remember, suppose if I consider this reaction X plus Y, this is all are 1 mole of electron is involved. Okay, but suppose there is not 1 mole of electron, I am trying to say, suppose here coefficients are 1, right? But suppose if we are doing the reaction that by multiplying 2 both sides, so now it will be 2a plus 2b equal to 2x plus 2y. So coefficient is changed, that means now amount of a and b both are changed. Similarly, these two may be 3 or it may be any fraction, everything is possible. Okay, so what I'm trying to say, when there is we are multiplying 2 or any other value, as del G naught, it is extensive property. Now extensive property, intensive property, these terminologies you find in thermodynamics. So what is the meaning of extensive? it is dependent on the amount of matter. Dependent on amount. But if it is intensive, then it is not dependent on the amount. So del G naught, it is as it is extensive. So when you are multiplying the reaction by 2, now you have to also multiply 2 here and also here, because now if n number of moles involved, as you have multiplied 2, this is also you have to multiply with 2. So ultimately this 2 is cancelled. So if in place of 2, if you are suppose multiplying with half or 3 or 4/5, any of these values you take, it doesn't matter, because in numerator and denominator you are taking the same value, so ultimately it will be cancelled. So I'm trying to say that E naught cell, it is basically intensive property. So don't think that when you are doing the reaction with coefficient 1, that is a plus b equal to x plus y, then the E naught cell that you are getting, and when you are multiplying by 2, then the E naught cell that you are getting, both will be different. No, they will be same, because it is not dependent on the amount of starting material you have taken. So whether you take 2A, 2B or 1A, 1B, it will always be same, because it is intensive property. But del G is not incentive property, so that is why it is dependent on the amount of substance. So from this discussion, it is clear that electrode potential, it is intensive property, does not depend on the amount of substance taken. Okay, so you don't have to worry about the coefficient of the reaction, because E naught cell, it will always have same value. In the denominator and numerator, same digit is there, so that is why ultimately it will be cancelled. So it is intensive property. So is it clear how E naught is related to del G naught and why this is intensive property? Is there any doubt?
No, ma'am.
Any doubt? Should I repeat? So we'll finish this with this problem. So here you will be able to understand how you are you can use the previous formula, that is del G equal to minus NFE. So here standard potential E naught value for two system given. One system is Cu2 plus Cu, another system is Cu plus Cu. So don't think these two are half cell reactions. No, it is not redox reaction. Just two systems are given, and 0.34 that is for first system, 0.522 that is for the second system. So you have to find out Cu2 plus Cu plus. So as if it is Cu2 plus, then Cu plus, then Cu. Okay, so here Cu2 plus to Cu plus, that is this value you have to find out, and the value Cu2 plus to Cu, this is given, this is 0.34, and this system is also given, it is 0.52. Okay, so how we will start? Suppose for this is system 1, this is system 2, and this is system 3. So del G3, that will be equal to del G1, because del G1 is which system? Cu2 plus to Cu. This is system 1. This is system 3, because Cu2 plus to Cu plus. Then 0.522, that is Cu plus to Cu. This system is 0.522. This is second system, okay, number 2, and this is number 1. So you can see, if you want to find out this, basically it is 1 minus 2. And it will also be clear if you write the equations. So for system 1, the equation will be Cu2 plus accepting 2 electron, it is converted to Cu. For the second reaction, it is Cu plus, which is converted to Cu by accepting 1 electron. Now if you deduct the second equation, what you will get? Cu will be cancelled. This Cu plus, it is negative, so it will be in the right hand side. 2 electron minus 1 electron, it will be 1 electron, and this is Cu. So now you are getting equation number 3. So 3, how you are getting? By subtracting 2 from 1, so that is why del G3 will be related to del G1 and del G2 by this relation. Now for the third system, here how many electrons involved? 1 electron. So we will write this formula, that is N3F E03 minus N1F E01 minus cancelled N2F E02. Now see, F will be cancelled. So ultimately E03, that is equal to, and N3 is 1 because 1 electron involved, N1 is 2 because 2 electron involved, minus 2 E01, and for the second system this is also 1 electron, so E02. Now minus sign, if we remove here, it will be E03 to E01 minus E2. So I'm just exchanging the negative sign. Now E1 is 0.34. Okay, 0.34 multiplied by 2 minus E2. E2 is this value 0.522. So after calculation you will see it will be 0.158. So it is matching with option 2. Okay, so this is one method that you can follow, and if you are want to follow this method, see, this range is given which is involving 2 electron, so just multiply with 2, and this range is also given from +1 to 0 and 1 electron involved, so 0.522 it will be 1. So from this range, if you are subtracting this, then directly also you can get the same value. So it is up to you which process you are comfortable with. If you are comfortable by drawing this type of diagram, then 2.0.34 minus 0.522 into 1. So you will get this value because this value is actually what. And you can also do this method. It is up to you which method you want to follow. But ultimate solution will be option 2. So this is positive 0.158. Okay. So this problem is clear, and you can understand how we are applying this relationship, that is del G is equal to minus N F E. If you are using not sign, it will be not for both. Okay. So by using this equation, we have solved this problem. Is there any doubt? So today we'll end the session here. If you do not have any doubt, thank you for listening.